Hello everyone, this is Ramakrishna Vadla, and I have Arnagiri Rajashekaran from IBM. So first of all, thank you SDC SNIA India for giving us an opportunity to share our experiences. So this is my consecutive third time presentation in such a prestigious conference. So we're going to discuss about predictive analytics and heterogeneous systems management using modernized services today. So we'll talk about what are the different challenges in data center management and what are the capabilities that storage system management should contain to handle such challenges, and what are the platforms we need to build to cater the storage systems management capabilities. So we need advanced cloud native services to build such a modernized management platform. And we also talk about use cases using predictive analytics, so which helps storage administrators and support persons to predict the issues even before they occur. Yeah, let's look at data center management trends. So if you look at in 2018, we had 33 zettabytes of data across the globe in various data centers. So this has been grown to such a level. So IDC has forecasted somewhere around 175 zettabytes of data is going to be stored across the globe, right? And out of this, 49% of data is going to be stored on the cloud. So that means that cloud adoption is going to be more. So it is very close to 50% of data that is going to reside on the cloud. And 30% of the data requires real-time processing. So which means that real-time monitoring is required for 30% or more than those devices, right? So given those forecasts, if you look at the challenges that we have in data centers, so the cloud adoption has been increasing. So because of explosion of data storage and network traffic, and the cloud, even the COVID-19 added more and more digitalization applications. The applications have been, modernized in such a way that monolithic applications have been moved to the microservices based architecture. So which requires a very different technologies like Kubernetes and containers and multi-tenant services as well. So to cater such a high volume of data, so the vendors are coming with very advanced technologies, components, and storage devices, switches, and fabric, right? So which also requires, it also comes with complexity in the management as well. Okay, that means that your storage management or data center management software should be able to handle this complex heterogeneous devices. And in the security area, so especially in ransomware attacks, we have seen billions of dollars have been lost in the past few years. And one of the research says that in 2019, on an average per business, people spend on ransom $133,000, which is a huge amount of money. Okay, and the current set of management tools are very old way of handling, whether one set of product or one vendor specific products is going to handle. But we need a very advanced storage management software. Okay, so if you look at the capabilities which required for storage management, includes different categories. Storage administrators requires more of monitoring health, performance capacity, and they should be able to notify about the tasks, the problems and risks. And whenever there's a risk happens, they should be able to open a ticket for the support. Right? And similarly, support experienced person, whoever is from the device owners, so they should be able to resolve the issues very fast using, using the remote collection of the diagnostic logs and configuring the best practices, and also if they should be able to predict, or they should be able to proactively find the issues, so that they can even fix even before they occur, and also meeting SLS as well. So another set of people who requires different requirements from the storage systems management or from the resource managers are the people who take decisions on buying the storage, buying the systems, right? So they should be able to plan the capacity, and they should be able to know what is the trend in the capacity consumptions and different workloads that have been onboarded in the data centers, right? And also the data placement optimizations. For example, we should be able to know whether how much of cold data is residing in the tier 0 or hot tier, right? And how do we get notified about this much of cold data has been residing in the hot tier, and that has to be moved to the next cold tier, right? So all these kind of requirements has to be embedded into the storage systems management, so which also requires very modern way of handling this. And yeah, so the traditional management softwares are no more is going to handle such a huge amount of data that is coming from various data sources, right? So we need a data-driven monitoring services, those that are going to use big data, machine learning, and some of the artificial intelligence technologies, right? And the traditional way of handling, the vendor-specific or product-specific services may not be sufficient enough to handle such a huge explosion of services and data in the storage systems, right? So to build such kind of management platform, so you need a microservice or latest technology such as Kubernetes based application, and also you need billions of or millions of telemetry data coming into the services from different storage systems and other fabric and switches from the data center, and you should be able to correlate all this data coming from different sources and find out insights into that. So that again, that requires a very big data lake architecture based on some of the NoSQL databases, which requires to be integrated with advanced machine learning or deep learning services such as IBM Watson kind of thing. And also you should also have the cyber resiliency, especially in the security of the data, whether it is in the data lake or maybe at the data which is flowing from different data centers onto the cloud. Yeah, so let's look at high level how does this cloud native services based architecture will look like, right? So if you look at here in data center high level, you have these different set of elements in the SAN network, storage, servers, and fabric or switches, and it will be coming from different vendors, right? So most of the customers will prefer multiple vendors for various reasons. So that is one of the a requirement that the customer's data center will have multiple vendor devices, right? So now you need a platform which should be able to handle the microservice architecture. So it will be mostly based on the Kubernetes or the Docker container. And if you look at the high level architectural microservice that are required to handle different tasks in managing the storage data, which includes like data collection service, which basically collects the raw data which is coming from each of these vendor specific devices, and then convert into some of the common object model, right? And you need scheduler and task services, which basically needs to schedule your tasks. And for example, I want to run performance collection for every 1 minute or 5 minutes, right? So you should be able to schedule those things, right? So once you have this data collection has been happened, so you should be able to store this data in a data lake in different services. One for the configuration data or inventory data of storage devices. Another one is a performance data service, so which is basically telemetry data flowing very frequently from the devices onto the cloud and then onto the data lake, right? And you need how does this microservices will communicate each other in the cloud environment. So there is something called Kafka or messaging stream, so which is going to be used across the services to be communicated, which is a very loosely coupled service as well. Now this data will go, the data which is coming from the different devices from data center, so that will be sent to the multiple storage devices based on the different types of data. So for example, telemetry data, so which is kind of delta calculations and some aggregation, those kind of data, time-based data will be best suited for to store in a Cassandra service, and along with some of the configuration data as well. And Redis, again, Redis is another data store where you can store some of the tasks and scheduler information. And there is also unstructured data which is coming from storage devices. For example, if a device is there that and it is generating a performance data, it could be in a plain text or XML or JSON, right? So that data is like kind of unstructured data, and you want to store that as a file in a object storage. You can use object storage as well. Okay, now you have got all the information collected from different sources, and it is stored in the data store. The next step is to make or derive insights out of it, right? So you can integrate these services with machine learning or deep learning services, and then you can also you can have the Grafana or Prometheus based dashboard, which will give the insights into your data, as well as because all the microservices are running on the cloud, and it is very important to track what's happening with your data. Okay, that's very important. Now let's look at microservices based infrastructure. So one of the platform that can be chosen is a Kubernetes. Let's look at the Kubernetes application, right? So it is an open source application which is used for container orchestration. So which means that provisioning of the container, and especially a Docker container, and service discovery, and as well as load balancing, right? So if lot of data coming in from the storage devices, and there are a lot of consumers which can be created within this cluster as a container services, and if you want to balance the data, the load which is coming from different the clients, then Kubernetes will take care of doing that load balancing for itself. Right? And also the auto scaling part of it. So for example, you have configured some set of services, and you're getting more and more load to these services, right? So Kubernetes can increase the number of services to handle such a high load, and at the same time the load has been decreased on the cluster. It will again reduce the number of containers, so that the infrastructure resources will be used optimally. And also the non-disruptive upgrades. So Kubernetes will make sure that you don't really need to turn down all the services while upgrade. So you can have rolling upgrades, or you can have version-based upgrades. So which basically require zero downtime. So that is again one of the challenge today we have with many of the services as an upgrade. And also it has very good integration with some of the backend storages using container storage integration, and you can integrate with that as well. So if you look at the high level, the integration for the microservice, so you need multiple services integration. One with the the Java runtime or any runtime that you need to process the requests coming from different sources of information, and you need integration with the Kafka, So that will send message to different microservice, and of course you need integration with the storage is based on the storage type like Cassandra, Cloud Object Storage, or any ephemeral storage devices. Arnagiri is going to talk about how cloud object storage can help us in this modern platform.
Thanks, Ram. So let me start with a brief intro about the object storage. So object storage is a data storage architecture for handling large amounts of unstructured data, such as images, videos, photos, documents, and other types of media and web content. So the objects in the object storage uses APIs such as so the native APIs used is HTTP-based RESTful APIs. So the object in the object storage system is accessed using the metadata is used to locate the desired object in the object storage system. So these RESTful APIs use HTTP-like commands like put or post to upload an object, get to retrieve an object, and delete to remove it. So the various cloud services running in the modernized storage management platform uses cloud object storage as a shared storage. So let me start with the data collection service here. So the data collection service connects to the underlying storage devices and then runs some device-specific commands, which generates the performance metrics and the inventory data in the form of a raw format. The raw format can be of type such as XML, JSON files, or could be a plain text as well. So these files will then be uploaded to the cloud object storage. Once the file is copied to the cloud object storage, a notification is sent to the common object converter service, which then downloads the raw protobuf file from the cloud object storage, and then it converts it to a common, Google-specific protobuf format. So the protobuf binary format is invented by Google, which is used for high-speed network communication between these services. So the protobuf payload is then uploaded to the cloud object storage. So as discussed by Ram in the earlier side, the Apache Kafka, which is an open source event streaming platform, is used as a communication medium between these services. So it uses publish subscribe model to generate and notify event messages. So the next service is the telemetry processing service, which downloads the payload from the cloud object storage, and then it creates some relationships on the data and does some post processing on the data, and then it uploads it back to the cloud object storage. The analytics service then picks this data from the cloud object storage and then fetches this data to the external analytics engine, such as IBM Watson or Apache Spark, to run some advanced analytics on the data. So if there is an anomaly is detected in any of the processing, like let's say for example, if a drive failure has occurred, or if there is a warning in the RAID arrays, then the notification will be sent to the alert service, which will then create a alert message and then send it back to the UI so that the administrator can take a corrective action on it. Okay, so we'll move on to the next slide, which is Cassandra for time series telemetry data. So the heterogeneous storage devices located in the data centers generate millions of telemetry data. So the database should be able to seamlessly handle this huge amount of incoming telemetry data, which is primarily performance metrics and inventory data from heterogeneous storage devices developed by different vendors. So Cassandra ideally fits for this purpose. So what is Cassandra? Cassandra is a distributed NoSQL database that can handle that provides basically continuous availability, high performance, and relay scalability that modern applications require. It also offers operational simplicity and effortless data replication across multiple data centers and geographies. So Cassandra can handle petabytes of information and thousands of concurrent operations per second. So it can scale up to petabytes of information, and it can also handle thousands of concurrent operations. So the data is partitioned on all the nodes on the cluster, and then custom data replication support is also available to ensure fault tolerance. And it allows basically allows zero downtime or offline for schema changes. There is no need to bring the service down to add or delete to basically alter or create a table, etc. in the Cassandra cluster. And it is basically a column-based NoSQL. So the driver support is available for all major languages such as Java, Python, C++, C#, Node.js, etc. Yeah. So I will handle it back to Ram to talk some of the predictive analytics.
Yeah, thanks, Arnagiri. So we have looked at different services and how we can make the storage management platform as modernized using some of the microservices which are available on the cloud, right? Now let's look at how we can derive insights from this storage, the data which is coming from the storage devices, and what are the different some of the use cases that you can really leverage. Maybe machine learning or some of the data science techniques, and we try to figure it out some of the issues using the data which is coming from the storage devices, right? So at the data center, we have, especially from the storage management perspective, so we have three layers of data, right? One is which is like very low component level data, which is like volumes, pools, enclosures, nodes, so disk IO group, and host connections and all. And these are all again next level aggregation go to the system level, all right, or fabric level. And then you need another level of predictive analytics at the data center level, right? So you need multiple levels of predictive analytics, right? So let's look at a few of the analytics that we can do using the latest technologies, right? So how do you do the performance anomaly detection, right? So we can see, if you look at the anomaly detection, performance anomaly detection. So you need historical data. So we need to collect large amounts of historical data to get a very precision-based values, right? That will give the accurate prediction. Okay, you collect the data and then prepare the data for anomaly detection, and then so using some time series based techniques like ARIMA based time series model, my machine learning model. So you train the model, right? And then so you can forecast it to next couple of hours or couple of days, and then next step is to once you got the data and you train the model, now you got the model, then you try to get the actual data set and get the data points for actual data. Then you compare. So if you look at the following diagram here, so if you look at here, so the blue line, if you look at the orange line is actual data that is flowing in, and the blue line is the predictor line, right? Most of the data is really matching. And but at one place, if you look at the place where we have a red dot, that is basically the actual data, so which is going beyond the actually predicted value, right? So there is also a gray area for both bottom and top of both the sides of this actual values. So it is called a confidence interval, which can be calculated based on the mean absolute error rate or standard deviation. So you can come up with like let's say 1.26 percentage of the error rate or something like that. Then that will give you like a plus or minus the actual values. Okay. So if a value that goes behind this acceptable range of confidence interval value, then you can think about that maybe some anomaly happened for that metric. Okay, so this has been done for read data rate, but you can do this for any set of performance anomaly detection. So you can have a continuously flowing in data and continuously train the model, and continuously it can predict and alert about anomalies in the performance metric. So the ARIMA has been used, but there are multiple other ways of doing as well. In the machine learning, you can use LSTM in deep learning as well. Okay, so now let's look at how will you handle your capacity if it is running out of space. How do you predict this one? Arnagiri was going to talk about that.
Thanks, Ram. So storage capacity planning is the practice of assessing and forecasting future storage requirements so that enough disk space can be purchased to meet the needs of users and applications. Effective capacity planning allows the data storage administrators basically to delay future disk purchases, which is important because the price of the disk continues to drop. So saving money, which can be used on storage resources, which can be used which can be saving money, which can be used to buy delay storage resources, can be unused, which can be better used for to allocate for which can be used to better allocate storage budgets on other items, etc. So typically administrators will receive a notification or an alert when the drive reaches, let's say, for example, less than 10% of free space. Less than 10% of free space, and the notification will be sent continuously until the full capacity is reached. So the time series data available in the Cassandra database can be used to forecast or to identify a future date in which the storage device reaches its full capacity or 100% capacity. So we can, the historical telemetry data of the last 3 months or 6 months can be selected, and then the capacity trends on the data and can be analyzed, and the model can be generated from the last 3 months or 6 months data. This model then can be validated by using different techniques, and then it can be trained. And by using some of the machine learning techniques such as linear regression, future forecasted date can be derived, which can tell when the storage device disk space is actually runs out of space or it reaches its full capacity. As seen in the example graph on my right hand side, so the forecasted date is the date in which the available capacity percentage reaches 0. So using this will basically enable storage administrators sufficient time. This will give sufficient time to the storage administrators to for a better capacity planning in the future. I will handle over to Ram to talk more about the ransomware attacks, how to predict the ransomware attacks.
All right, thanks, Arnagiri. Yeah, so in cyber resiliency, one of the problem we have is on ransomware attack. So as per some of the research that happened in the past few years, so there is billions of money has been paid as a ransom for ransomware attack, right? So it has been happening very frequently, and we have various solutions to handle ransomware attacks, right? So but it would be good if you can come up with a solution or predict the ransomware before even occur. That would really help our customers to save some money, right? And also, especially the data. So, right, data is very should be very secured, and we should not lose that. So, ransomware is a small software that will be executed on the victim system, and it will either lock or it will encrypt the data, and then it will ask the enterprises to unlock or decrypt the data, right? So there are three types of ransomware. One is like locker ransomware. What it does is it blocks your computer, and it just locks your computer. It will not allow you to access your data inside your computer. Another type of ransomware is crypto ransomware. Basically, it will makes your data unusable. You will be able to log in, but your data is encrypted, and whenever you try to access any important file or any data, so it will ask you to pay ransom, and it will give the decryption a key, right? Another type of ransomware is basically the combination of both. It will lock as well as it will just encrypt your data. So within crypto ransomware, there are three classes. Okay, so the core model is same. It will basically opens the files and reads the files, encrypt and writes it. But how they will read and write is different based on different types of ransomware. Okay, so in first class A type of ransomware, it basically opens the same file and encrypt the same file and writes it to the same original file. In class B of ransomware, basically it will move the files to a different location. You can think about if your system has a cloud access, the file will be moved to the cloud, and it will run the encryption there. Again, it will send back to your system, right, to the same location. So that's what it do. And in case of class C, it will read the original file, encrypts it, and again writes it back, but it will delete the original file. So, but the sequence of steps are same. Okay, so let's look at how do we detect this ransomware. So if you look at these crypto ransomware steps, it will search or list the set of important files. Important files can be like frequently accessed files, right? Or maybe some your local my documents or anything that is related to your project or your personal data, right? Or our company corporate data. So those kind of files it will just search, and it will try to read a file. Right, first it reads the file. That is like you can think about high sequential reads, right? And then it will start encrypting the file. Basically, there is no activity on your file. On your system, and after that it will start writing. That is kind of again our high sequential writes to the disk or volume. Okay, so now if we have this kind of pattern, right? So if we have this kind of pattern, so let's look at this diagram here, right? So if you look at the same set of so if you look at the same set of data here, so if you live till 8 o'clock here, the read and write pattern is very common, right? It's very same. And from then onwards, the blue line shows read IO, and orange line shows write IO. So what's happening is, if you look at here, the read IO is more. The read IO has been spiked up, and it will be there for there some time. That means that keep on reading the data. But during that time, your writes are normal, right? Again, that the ransomware stopped it. Again, the read has been started, and write has been stopped, and read has been started. And this pattern continues. If you look at here, high reads, high continuous reads, and then low writes. Again, high writes and low and normal write, right? So that is kind of it's kind of anomaly that you can detect using the time series algorithms, and then that will give some hints or some prediction about, there is something anomaly happening which is not a normal thing. So that will allow you to figure it out. Okay, so there is anomaly has been detected, and then customers or storage support guy can look at that particular volume and see what's happening with that. Okay, so that will help. So there are ransomwares which will also do the parallel read and write. So, but we need to come up with a next level of algorithm to figure it out. That okay. So this will help customers predict if there is a ransomware is going to happen on your data. Okay. Let's look at next use case, noisy neighbor host detection. So in the current virtualization environment, so most of the volumes in a cluster will share same hardware infrastructure, right? So if one of the volume is busy because of host which is having some high workloads, which is running a lot of CPU and a lot of reading of data, the volumes which are in the same other volumes which are in the same cluster might have low performance, right? So it might negatively impact on these volumes. Okay, so that means that it will have the victim volumes will have high response times because of one of the volume which is attached to a host, which is having a lot of reads and writes, right? So how do we detect a host which is causing this problem? Right, so we can use some of the performance counters for volume, pool, and host, and we try to predict, or we can find out, okay, this particular host is causing the problem. So let's look at how we can figure it out. Noisy neighbor host. So we will identify a volume with high response time thresholds. This it can be like the threshold has been exceeded beyond the certain limit, or you can also use time series based anomalies detection. So for the volumes which has continuously seeing some anomaly in the response times, then you find out which pools those volumes belongs to. Okay. Now the next critical point is that what are the metrics that I should choose from pools so that I can figure out which host is causing the problem, right? So you choose a certain set of metrics based on some of the basic understanding of the correlation between pools and host metrics, and try to run the correlation. Okay, till you get a proper correlation between pool metrics and host metrics, and there are certain set of correlation techniques like Pearson, Kendall, and Spearman. So you can run some of these correlations, and at some point in time, you will find a proper metric, and you will find a very high correlation between a pool and a particular host. So that host can be considered as a noisy neighbor, which is causing the problem. Okay, so you can generate a heat map. So based out of these pools and host metrics, so that will give you the high correlation between the pool and host metrics. The host with the highest correlation, it can be a host which is causing the noisy neighbor problem, which is basically hindering the performance in the other host or volumes in the same cluster. Okay. Yeah, this ends our presentation. If there are any questions, we're happy to take them. Thank you very much.